We are breaking into the giant Catnip vault. Bypassing these security systems depends on our ability to leverage the predictable laws of mechanical physics. A massive block of heavy cheddar is obstructing the main entrance. Moving a weight of this scale requires a calculation of force rather than simple exertion. In a laboratory setup, the pulley itself is lifted along with the object. This means the weight of the pulley must be added to the weight of the cheese. Our total resistance sums to 120 grams. To operate the system, we anchor one end of the rope to the ceiling, loop it through the movable pulley, and pull upward on the spring scale. The configuration distributes the load across two rope lengths, the anchored side and the pulling side. The 120-gram total weight is halved, requiring a pulling force of exactly 60 grams. The movable pulley functions as a primary effort-saving device. To cross this chasm, we must manipulate a ceiling-mounted transport mechanism, a system that functions exactly like a common clothes-drying rack. This is a composite machine. We can identify its mechanical components by observing which parts remain stationary and which parts move during operation. The top fixed pulley changes the force's direction without reducing the load. Pulling downward creates upward motion. The lower movable pulley travels upward with the load, performing the heavy lifting and reducing the effort needed to raise the system. By combining these two types of pulleys, the machine allows us to change the direction of our pull while simultaneously saving effort. We have reached the inner door. The control mechanism is a concentric dial featuring a large outer wheel and a smaller inner axle. The dial's geometry is precise. The outer wheel's 6 cm radius and inner axle's 3 cm radius form a 2-to-1 ratio. Functioning as a circular lever, the center is the fulcrum. The wheel acts as the effort arm, and the axle is the resistance arm. The internal bolt, weighing 40 grams, is attached to the smaller axle. Because the effort arm on the armor wheel is twice as long as the resistance arm, applying just 20 grams of force to the wheel will move the bolt. Applying force to the wheel side of the system always saves effort because the effort arm is longer than the resistance arm. A security gate is dropping. The control line for this gate is spooled around the large outer wheel, meaning we have to turn the tiny inner axle to pull it back up. This forces us to operate the lever in reverse. The 3 cm axle is now our effort arm, while the 6 cm wheel becomes the resistance arm. The mechanical cost is heavy. To lift the 40-gram gate by turning the small axle, we must apply 80 grams of force, double the weight of the object itself. However, this increased effort comes with a specific mechanical trade-off, a gain in speed and distance. Because the outer wheel is larger, a small rotation of the axle causes the outer wheel to spin through a much larger distance. The heavy gate is pulled upward instantly. Engineering success depends on choosing the correct ratio, trading distance for effort, or effort. Calculating the specific weight of a movable pulley or the radius of a wheel and axle allows you to dictate exactly how energy flows through a machine. Understanding these numerical ratios turns a simple physical struggle into a solved engineering problem.